So we talked about the abstract data type list, which is a sequence of 0 or more elements of a particular element type. Element type is what the user supplies. And let us say the length of the list is some n. Elements go from A1 to AN. Each AI is of type element type. And now what I'm going to do is I'm going to show you a list of integers which can be implemented using both a linked list and an array. Let's see how to do this. Okay. What we do is the following. This is what we talked about as a set of operations that make up a particular list. So this is a general list where I can insert anywhere, delete anywhere, retrieve any element from anywhere, print the entire list, create an empty list, and find the first element in the list, and so on. So if you look at it from a different perspective, these are the operations where you put something into the list, and all these operations retrieve various things about the list, okay? And or modify the list for that matter. Now this could be an array implementation of the list where the elements are found in an array. The list is stored in an array. So what you do is you could, this could be underneath, for example, the abstract data type where the data type is actually hidden could be an array representation, or it could be a linked list representation where you have a pointer to the header and you access the elements in the list via the header. I use a dummy node because it's a bit convenient to perform certain operations, which I will show you in a little while. So now what we'll do is so you could have an array representation or you could have a linked list representation. But the user application should be able to work in the same way with both the array representation and the linked list representation. Let's see how this happens. Okay, let's say this is the linked list representation. So notice that I've created a structure where element type is of type integer, need not be integer, could even be a record, as we saw nested records, nested structures in the last class. It could be a list of names, it could be a list of addresses, list of strings, whatever you want. And notice here, a variable called position is defined, which is a pointer to this list, okay? So this position is going to be useful for us when we implement certain operations. Let me see how. So what we're saying is, what are the various operations that we have? Position points to the private, for example, because it's a linked list representation, you only have a pointer to the head of the list. So position points to the head of the list. Then I can create an empty list, doesn't return anything. Or I can insert an element X at position P, delete an element at position P, and I can get the position of the first element, position of the last element, find the end of the list. What are the next position to the after P, which is the next position, and so on. And there's various operations. I only implemented some of them over here. So what do? I create, as I said, when I showed you the picture, that I create a cell with simply a null node. I create a new cell type and list pointer next is equal to null. And what I do is when I'm inserting an element at position P, I actually insert it at P pointer next. There's a good reason why I want to do this. Let me show pictorial about what I'm doing. So there's an empty here, and let's say I want to insert it at this position over here. So you expect that I will be replacing something here. Instead, I will insert it at the position next to it. As long as I ensure that when I'm retrieving this element. When I say retrieve at position P, I'm good. Why do I do this? There's advantages for me to do what's called a delete operation. It's a single line. I don't have to keep track of who, from where, suppose I wanted to delete this element, I must take this pointer and update it. Suppose I want to, let's say, delete this particular element, I'll have to know where this pointer came, which was pointing to A, and then update it. But here, because I'm storing at the next position, I can simply P pointer, next, P pointer, next, because I'm storing it at P pointer next. So I just update that particular address and the deletion operation is effected. Okay. Then, so this is exactly what I'm showing over here. So this will just simply point over here. When I say delete an element at position P, it means delete the element as P pointer next. That is the bookkeeping that I do. And first we'll return the list head, and uh, end will give me the end of, while P pointer next not equal to null, I return the value of P, because that is the end of the list, because P pointer next is already a node that is there where I will insert an element. Okay, I can insert an element at P pointer next. Okay, so for insertion and deletion, it's nice to have a dummy node in my list. And next will return, of course, P pointer next. There's no problem with this. And print list simply prints all the values in the list. Notice that I start printing from the next node, because that's where I have the elements in the list. Okay, so now I'm going to show you another implementation with arrays. What did I do here? Remember earlier we did type def int cell star here. Here on the other hand, what we're going to do is type def int, because it's an array. Same, so we aliasing into position. There was cell star was alias to position. So position refers in both cases to a position on the particular list. And element type is same value here. It could be a structure if you wanted. And notice that all the operations look the same. Insert at position P, delete item, make null, print list, end. Let's go back and look at this. They look identical over here. Notice that. Insert, delete list, first, end, next position, print list, every one of them. Okay. And what do we do here? And all right, I've changed small e to capital E here, but that doesn't really matter. And now what I'm going to do is, what are the various operations now? Creating, make null, creating an empty list creates an array, list which is represented by an array of cell node of some size 100, or you could even, I'm not passing any argument here because I want to be consistent with the linked list representation. And insertion, for example, what does it do? At a position P dot value, and then it updates, just like what we did in the insertion sort for that matter. That's exactly what insert is doing over here. And print list just prints the elements, same identical interface function for both of them. End will give me the location of last node plus 1, and delete item will simply update all the elements and then reduces the number of nodes. Similarly, insert will increase the number of nodes that are there. I keep track of the last node as part of my, okay, 1 minute. Private, I will keep the last node and also keep the pointer to the array which represents the list. Now here, what I have is, I have an application. This application will work seamlessly with either implementation of lists. That's the most important point. As long as I include the appropriate .h file, which is represented by something like this. Here, this is the .h file, which is the class definition file. As long as I include this, it's going to be no problem with the type def and everything together. As long as I do that, and it is transparent, you just like you do a standard io.h, I do some list list.h, and it should all work hunky-dory, irrespective of whatever you are trying to do. And notice that the same set of operations can be performed on using both the types of lists. So what did we achieve by this? We actually were able to hide the internal representation of the list. We used two types of representations. One was a linked list and one was the array. And what we have shown is, in either case, it is possible for us to do operations without actually knowing how the underlying representation of the list is. So we will stop here, and then We will look at stacks and queues in the next class. And before that, of course, you can do a lot of problems with this. You can use lists to represent sets, perform the union, perform the intersection, perform the complement. And you could also do merge two lists and then purge duplicates in the list. All this can be done simply with list operations, as I already showed you one example. We will stop this over here. Stop the class.